Here we go. Our sixth objective on practice test B is a distributed practice about chemical and physical changes. What we'll be looking at is making a decision based on a driving force. Can we use a tool, either an activity series or a solubility table, to help us predict if a reaction indeed occurred? So we have three lines to kind of help us remember that there's a part A, part B, and a part C to address for each one. In the first line, we'll indicate if something is a physical or a chemical change. We'll explain our reason for the choice, and if it's a chemical change, we'll go ahead and write a reaction. We don't need to write a reaction if we made our decision that it was physical. Part A and B, in my mind, go together, and C and D go together. Part A says nickel is dropped in water, and part B, potassium is dropped in water. You can count on that pattern on test day as well. It'll be a metal dropped into water. The pattern here are single replacements, when an element is dropped into a compound and water is treated as a compound. So the tool page that we need to consider is called the activity series. In an activity series, just to try to remind us, the strongest of strong being lithium, we call that the most active, all the way down to the weakest of weak, that would be gold. So in our first example, the letter A, it says nickel dropped into water. In order to predict if this is active enough, I try and find nickel on the activity series. I notice that it is above hydrogen, and that's what water starts with, but it falls in the category of nickel's only strong enough to act with acids, but not with water. Recall that the top area, and that's a little star down underneath the little note, the active metals from lithium to sodium can react with acids and water, but from magnesium down to just above hydrogen, it's acids only, and that's where nickel falls. So nickel dropped into water is going to create a wet piece of nickel. There'll be no chemical change. So I'm going to write down that my choice is physical, and that takes care of the part A. It is a physical change. And the reason for my choice, the activity series. I used the activity series to make my decision that nickel's not strong enough to react with water. So therefore, I'm not going to bother writing of chemical reactions, and I'll leave that third line blank. But in letter B, this one is giving me a metal called potassium. Potassium dropped into water. I noticed that on the activity series, potassium is quite high. It falls into the area that these are strong enough not only to react with acids, but also with water. So based on the location of where potassium is on the activity series, this one would occur. We would have a chemical change. And again, the same tool was used called the activity series. When potassium reacts with water, for singles and doubles both, I like to write water as HOH. That helps me predict how the potassium displaces the hydrogen. So just visually, you'll see that the hydrogen gets kicked out. And when it does so, it's a diatomic molecule, H2, and potassium hooking to hydroxide, KOH, with a +1, -1. So when we balance, we end up with a 2 to 2 to 1 to 2 stoichiometric ratio. A and B, you can count on the pattern, will be single replacements. You'll use your activity series to decide will the reaction occur. As mentioned, letters C and D also go together. These patterns of change will be a double replacement. And what we'll need to decide if we had a driving force for a double replacement. And I remember pointing up here to this poster where it says driving forces could include making a gas, making a water, or more probable is a precipitate with the help of our solubility table. So another good little note over here, in order to predict if a precipitate formed, we'll need to find that solubility table and find an insoluble product. Let's read through the letter C where it says ammonium carbonate placed into magnesium chloride. In the pattern of double displacement, they're going to exchange last names. Now it might be easiest to just take a look at the products and decide, can you find a driving force? If ammonium, who's a +1, carbonate, who's a -2, so the first reactant, ammonium carbonate, placed into a solution of magnesium chloride, and based on charge, that's MgCl2. For this particular pattern, I like to write the products out and then decide, can I find the driving force? So if ammonium goes to chloride, we'd get 2 units of NH4Cl based on charge. And magnesium goes to carbonate, and based on charge, we get a +2 -2 MgCO3. So if this indeed is a chemical change, it would be represented by this pattern. Ammonium carbonate, magnesium chloride, produce ammonium chloride and magnesium carbonate. Now neither one of the products is a water molecule, neither one of them talked about bubbling, so I need the solubility table to make my decision. In the solubility table, we could check out the first product, ammonium chloride. When I hook ammonium to chloride, that's soluble, so that's not a driving force. The other product was magnesium carbonate, and finding magnesium carbonate, insoluble. So there is a driving force. We're looking for an insoluble product. Now I can circle this and label that as my driving force, which lets me know it was a chemical change. And the tool we used for the second answer to explain my reason, I knew it was a chemical change based on the solubility table, finding my precipitate. So I can let you know it was a chemical change just by circling the driving force and labeling that as an insoluble product. Letter D will also follow a double replacement pattern. Let's take a look. If magnesium chloride is placed into sodium sulfate, magnesium chloride, based on charge, we've got MgCl2, and sodium sulfate, based on charge, we get Na2SO4. If a reaction occurs, the 2 positive ions exchange, we would create magnesium sulfate, Mg is a +2 as well as sulfate a -2, and then 2 units of our sodium chloride, +1 -1. So if this is a chemical change, we need to find a driving force. Again, neither one of the products is a water. Neither one of them are a gas. They're an aqueous solution. So we have to turn to the solubility table to see if we can locate an insoluble product. MgSO4, I'll look up first. Magnesium hooks to sulfate. That's green. That's soluble. The other product was sodium chloride. Na hooks to Cl, also soluble. Can't find a precipitate. Therefore, there is no chemical change. It's a physical blend. So I'll label this as a physical change. There's no driving force for our double replacement. The last pattern, letter E, calcium and sulfur are placed into a test tube, and here's a critical part, and heated. This pattern of change will always recommend